A very warm welcome to our lecturer, the as Dr. Zakri Abadi Baharuddin, and today we are going to present about the Lab 4 DC high voltage measurement and monitoring system. And this is our group members' name, which is Vasandan Analaki Rajendran and Nusha Memi binti Saberi, and myself Kuganesh Analaki Krishnasamy. So the objective of our lab is to construct a parallel DC high voltage measurement using kit control 4.0 and picoscope 3000 series, and also we also familiarize the procedure for setting DC the kit control 4.0 and picoscope 3000 series, and last week able to compare and analyze the DC value obtained from the kit control references and picoscope 3000 series display. As we can see there, this is the puzzle layout for the construction of the parallel DC high voltage measurement using FC and picoscope for the previous lab 3 section. And as we see the layout, the transformer is the main thing and will be connected to the capacitor 100 picofarad and will be connected to the parallel system, which is 20 milliampere resistor diode, and then connected to the capacitor, which is 25 nanofarad, then connected parallel to the 2.4 kilo ohm resistor and 280 mega ohm. And after that, the end of the 280 mega ohm, the long coaxial cable is connected to the secondary part CM and continuously connected to the BNCT junction. So the BNCT junction straight away connected to the frequency converter DM1 and picoscope. So there will be another parallel secondary part CM for 100 picofarad of the capacitor, which is connected from the capacitor 100 picofarad, the BNT junction, and the secondary part of CM is connected to the frequency converter DM and picoscope. This is the schematic circuit, which is the DC high voltage parallel circuit, and there will be a simple explanation is from the transformer, the 100 picofarad is connected to the parallel and is connected to the 20 milliampere parallel series connection, and also connected to the capacitor 25 nanofarad, and also connected to the parallel resistors 2.4 kilo ohm and 280 milli ohm. So from the frequency converter of CM, it will be connected to the picoscope and frequency converter DM1. It's a parallel. So for the safety rule reactions, there will be a discharge and ground rod used to the manual discharge of high voltage components, and also the safety gloves must ensure every time enters. Use hand gloves due to the withstand up to 30 kilowatt. So here the connections of the layout previously. This is the transformer, which is connected to the 100 picofarad capacitor and also followed by the parallel connections. Then the long coaxial cables is the capacitor is connected to the 40 cm of the coaxial cable. Then the 280 milli ohm resistor also connected to the 40 cm of coaxial cable to the secondary unit. And the third pictures explain about the BNCT junction connector, which is connected to the VM1 and DM1 of the FC cabinet using long coaxial cable, and another connection is to the picoscope with a long axial cable. So the fourth picture is a secondary part, which is there is a two secondary part in this parallel AC high voltage and DC high voltage connection. The CM is connected to the banana connectors, which is connected to the BNCT junction, and followed by the fifth pictures. The capacitor can be used as an energy storage capacitor for generation of impulse voltage as smoothing capacitor for the DC generation for 25 nanofarad, and the 20 milliampere diode is a high voltage diode which can be used for the impulse and DC high voltage configuration. The diode consists of the protecting resistor and a high voltage diode, followed by the 2.4 kilo ohm resistor. The high inductance resistors are used for the wavefront resistors. This is the 2.4 kilo ohm resistor is also used for the discharging purpose, and followed by the 280 mega ohm, the resistor which can be used as a high voltage unit for the DC voltage divider.
Okay. For section 2, we explain about the source of kick control and picoscope. There is power input connection. 1/2 is the cable termination for power input, that is the customer responsibility. There is a 1 stroke PE, stroke 2, stroke 3, stroke PE and stroke N. The 3 phases have to be connected to 1, 2, 3. The PE is for the ground of the input cable. If the input cable provides a neutral ground, this can be connected to neutral, but it is not needed. For input protection, there are varistors between the 3 phases and the PE. The figure shows the connection of input power of kick control. Next is primary side of the transformer progress. The 2 figures show the series connection of primary windings and parallel connection of primary winding at transformer. 2/220 kV at primary and secondary transformer. There are terminology parallel and terminology series. If we do terminology series, that is 2px to 1 2pu, it will get 100 kV at secondary transformer. Secondary transformer is the potential from grounding point to higher point, that is 0 volt up to 100 kV. If terminology are connected in parallel, the secondary transformer will present as 220 kV. Third is system monitoring of secondary side of the transformer with 8 slots. The terminal PN1 until PN6 is terminal for measurement, that up to 7 volt RMS. There is 2 channels for AC, which are VM1 and VM2, while channel 1 is VM1 slot is connected to inside the kick control. The other slot, which are declared as VM3, VM4, VM5 and VM6, are for DC. Next is alarm system. This is the circuit of alarm system. On how the connection for alarm with source, which the pin 7 is the common of potential free contact. For pin 8 is the switch potential free contact for the red lamp, while pin 9 is the switch potential free contact for green lamp. Last is pin 10 is the switch potential free contact for horn. Then for configuration of calibration section, the series number which is S/N is 223-41026-04. For divider ratio is 16951.1. For measuring setup for kick control, the VM1 and VM2 is the for AC. In the cable slot show slot RMS and slot RMS1 is for VM1. For slot peak screw square, slot RMS2 is for VM2, while slot measurement 3 is for VM3, slot measurement 4 is for VM4, slot measurement 5 for VM5, and last slot measurement 6 for VM6. Firstly, when look at the alarm at the software is red color. That means it is not ready to do any injection. Then click the reset button and the alarm show the green color that allow to do injection in the system. After that, go through setup, then click the customer setup. The cable will pop up and set the 0.1, 1, 10. Next is activate the 2 channel which are VM1 and VM2. For slot 1 was set V, then for calibration was insert the divider ratio value, which is 19651.1. Last step is save the setting. Last for section 2 is about setup for picoscope. First step is name the file as kit control 300. Then for acquisition sample was set 100k at point. It is due to get the better graph for result. Next is sampling interval, which is for accuracy of measurement. It is set between 5 micro to 50 micro. Also can be adjusted the cursor to get the best value. For now, the preferred value is 10 micro. After that, go through with trigger active is to impulse and capture is light to turn on. Then the channel A, B, C and D is activate because the picoscope have the channel A, B, C and D. AC coupling also activated. Besides, auto range will activate based on the suitable of the graph. This is adjust for value of amplitude or peak value. For divider ratio was set 19651.1 and for offset was set at 0 because x-axis is start from 0. The AC for RMS, RMC and peak also was activated. Next, the channel A was activated by click the AC. Lastly, the restart button was clicked to set up all those steps.
Comparison for analyzing the reference signal and display signal. The output voltage percentage was increased by 10% consecutively starting from 0% up until 50%. The reference signal from the kit control and the display signal from picoscope is recorded. The percentage of error is then calculated using the formula. The frequency remains same, which is 50 Hz throughout the experiment. Analysis. From the table and calculation, there are some minor error occurring between reference signal and display signal. This discrepancy is due to instrumentational error. This is because it depends on the sensitivity of equipment to measure the value. The discrepancy also caused by unstable power supply being injected into the system. There are various components which causes the unstable power supply. The residual potential difference in the capacitor also contributes to the minor differences in the raw data reading. Rectifier consisting of diodes which are in forward bias is used to change the AC voltage produced into DC voltage. A smoothing capacitor is used to reduce the ripple in the DC voltage. A resistor is then used to damp the voltage that is going through the earthing system. This is to prevent any long-term damage to the earthing system. To measure the DC voltage, a resistive load is used. At the end of experiment, discharge process is done to make sure all the residual current is grounded and then system is safe to be handled. Conclusion. Precision high voltage measurement require careful attention to the environmental conditions, the proper application of high voltage probes and basic function and features of the meter. Careful selection of highly functional meter can provide flexibility in application. We were also able to identify and use the correct equipment for generating and measuring DC high voltage. The safety precaution is also highly practiced during this experiment to prevent any damage to the equipment and the person handling the experiment.